Okay, so welcome everyone to a new Engineering Digital Twin Talk. Today we'll have a discussion by Andrea Matta from Politecnico di Milano. For the next session on 7th of April, Jacqueline Lemon will join us, and soon we will announce our next speaker for the 5th of May. So as I mentioned, today we have Professor Andrea Matta. He has published more than 190 scientific papers. He's also editor-in-chief of Flexible Services and Manufacturing Journal since 2017. His research area includes analysis, design, and management of manufacturing and healthcare systems. And today he will give us a presentation about autonomous digital twins for optimal control of discrete event systems. So Andrea, thank you very much for your presentation today. And yeah, now the floor is yours.
Okay, thank you for this nice introduction. I will share my screen. Should first, okay, now
I stopped it.
Can you see my screen?
Yes.
Perfect. Okay. Okay. So let me introduce this talk. The title is, of course, related to digital twins. Digital twins for discrete event systems. And I will show what we are doing in a European project that is called AutoTwin to develop a platform to build digital twins that can be generated starting from data and adapted always starting from data. So let me first mention the project. So this is a European project that is mainly related to circular value chains. So the goal of the project is to develop these autonomous digital twins for circular economies, okay, that are, let me say, complex discrete event systems characterized by several actors exchanging physical flows, products, and components in the supply chain and the information flows. You see the countries that are involved and the partners that are involved. And I'm the coordinator of this project that started more than 2 years ago, and we are in the last year. And today I will show to you the results that we got until now. Just a few numbers about the project. We have 13 partners, 8 countries, started in December 2022, 3 years. Totally for this, you see here is more than 800 person months. This is corresponding to 24 people working full-time for 3 years. So this is the amount of activities we are dedicating to this project. And then you will see some other details of the project. Now, this is the outline of my presentation. I will first motivate the project, and then I will move to describe the main concepts of the project, and then the use cases that we are working on, and then I will share some project results, as I said. This is a presentation mainly about at consortium level. So I will present the results that are not only mine, of course, because I'm the coordinator of a big consortium. So I will present the results that all consortium reached until now. Okay, and of course, if there is an interest on some specific topics, we can organize other seminars, even more technical. Now, just what we want to attack. I want to attack circular economies. I don't know if you are expert in circular economies, but I will be very fast. Mainly, we are moving from the traditional model, take, make, use, and waste products Generally, we take resources from the ground, we make products, we use products, and then finally, when we don't want to use products anymore, we waste products. And we are moving to non-linear processes because we start recycling materials. We are returning materials again to make again the product, to reuse products, to repair products. Mainly, we have a non-linear, let me move this. We have a non-linear economies in which products you see move from their use to share reuse, to repair, refurbish, and so on. Okay, so we want to manage this, we want to help to manage this circular value chain in which we have several actors interacting and exchanging information and material flows. The main features of the circular economy that we want to represent are these ones. First of all, we have to take into account of the efficiency of resources. There are many resources like production facilities, transportation facilities, and so on. In this non-linear, let me say, value chain, we have products that that might have a life that is very, very long. So we have a longevity of products. So we have to follow these products for some weeks, but also for many years, okay? So that I can predict when this product can come back, and then I can optimize my production. Then, of course, the products come back. So you see several loops here. You see here in this circular value chain, the right side, but also here you have several loops. And as you know, when you want to model the loops, mathematically is always, let me say, not easy because you are catching, you have to take into account the correlation among events. And then stochasticity. We have a lot of stochasticity in this circular value chain. Well, of course, we have stochasticity in all the phases. Here you see the phases from resource extraction to production, distribution, consumption, dispose. So each of these phases might be stochastic, but this is traditional. Any value chain is like this. Here you see the loops. If products after consumption come back to production, this is a short loop. You might have a medium loop here in the beginning of the production, or a long loop, for instance, for recycling or something like this. Now, where stochasticity might come from? First of all, the nature of the project, of the products. When I have a product that come back here in production, probably it's very difficult to know what are the materials, what is the composition of the physical object. So this is like an uncertain element that we have to manage into production. If I'm able to track and trace the products along the life, I might reduce this risk. Also, the consumption phase is highly variable because during the consumption phase, the user is using the product like a car, the battery of a car, no? And you see that during the consumption phase, generally after the consumption phase, the product returns back to in the short loop, for instance, or in the medium loop. And we don't know when it is coming back. So assume that now we are the manufacturer of the product. Here I have the distribution phase and the consumption phase. The time between when I finish to produce the product and when the product comes back to me, you see, so the time for the loop, for a cycle, is called the return time. And if I'm able to predict the return time, then I can, let me say, optimize my production facility because I can predict when a car is coming back or the battery of the car is coming back, so I can prepare my facility. And so this return time is stochastic, but I can reduce the stochasticity if I get information from the consumption phase, because you see, the more information you have, the smaller the variability of the return time that we can manage. And another source of stochasticity is the quality level. After the consumption phase, we don't know the state of the object and the cost needed to bring the object back to the quality level. And in this context, it is very well known that digital twin can be a business accelerator. And here you see some data showing also the digital twin market that can be very important in circular economy. So that was a big motivation for our project. However, digital twin is not a very nice technology to be maintained and to be developed, because you need high skills. It's not easy to develop a digital twin. Imagine the circular economy, they will last for years, and they will be very dynamic, because a new production facility may come, a new actor, and so you have always to adapt to maintain this digital twin. And so you need skills, and can be also very, very expensive. And so here the concept is mainly what we want to do. We want to support the circular economy in what we call green gateways, that are the points in which we make decisions. So we make green decisions. For instance, here we had to decide if the product has to do a short loop or a medium loop, for instance, or should go to dispose. How can we support the decision maker in the green gateway? You see here we are the decision maker, and we are using a digital twin. The digital twin is trying to make predictions about the return time of the product, about the quality of the product, about the current situation of the material and information flow of the production facility, so that you can, let me say, make the optimal decision for the circular. So what we want to do is to build this digital representation of the actual loops to support the decision in green gateways. Just a few, let me say a few words about digital twins. Okay, I think you are expert in digital twins, so I will be very short. We are taking into account 4 types of digital twins. So product digital twins, very related to a physical product, where 3D dimensional representation is very important, and you can make a lot of engineering analysis. System digital twins, in which you have complex systems with many actors, many information nodes, and many physical flows that are crossing. And we are focusing in the project on this type of digital twin. Then we have a biological digital twin, for like a fish farm or part of human bodies or something like this. And the digital twin that are the environment digital twins, in which here the space of representation plays an important role. Our project is focusing more on system digital twin, even if we have also an example of a product digital twin. We are considering the main features of digital twins, and we think that the digital twins must have 3 basic features. Of course, the digital twin must be digital. It can be very trivial, but it's like this. Should be descriptive. So the digital twin should provide information and knowledge about the physical entity, how the physical entity is changing, and let's say anything that may help the manager of the physical entity to improve the performance or to keep the performance at a certain level. The third basic feature is that the digital twin should be synchronous, so it should be always aligned, let's say, at any moment to the physical entity. Any moment, of course, depends on the application. Can be for a foundry, any moment can be every day, to have a synchronization once per day. For the control of an engine, it should be milliseconds, of course. So without one of these features, according to this, our definition, a digital model cannot be considered, let's say, a digital twin if it's not synchronous, descriptive, and digital. And then we are considering what we call the advanced features of the digital twins that a digital twin might have, but it's not mandatory, okay? It's not needed. Digital twin might have these advanced features if the business case is important, okay? It's important to be predictive, prescriptive, and so on. The first one, of course, is predictive. The digital twin can make predictions, estimates of states, and estimate of the impact of some actions. It might have also the feature of prescription. So it might help to close the loop, the control loop, by suggesting decisions. It might have the adaptive feature. So it adapts to the physical entity. In our project, this feature is very important because a digital twin, you know, might be very, very expensive. So it is likely related to an asset, an important asset. And important assets have a long life duration. We are talking about years. And it's quite natural thinking that the physical entity will change in weeks, in months, and in years. So if the digital twin has to follow the change of the physical entity, you know, you must have the alternative to have programmers offline that are changing the code. In our project, we are doing this, let me say, online from data. So we are trying to develop models that are adaptive. And the last feature is the granular related to the granularity. A digital twin might use different levels of information and different models. So these are what you call the advanced features of digital twins that we are trying to capture in our digital twins. The project is moving from data. So we start from data. And the ambition is to build the models in the most automated way from data. And then thanks to this model, we can make decisions that we call green because we are talking about sustainable economies. And then after we make decisions, then we come back to data. We see if data are according to the new decisions. And again, you see the loop here, okay? If something changing in the system, we should be able to get to realize it with the data, with the new data, and so adapt the models and then adapt the decisions. If you have questions, I think you can also ask questions now. No problem. Now, so these are the three pillars of AutoTwin. We have, let me say, one work package that has to manage all the data. So another work package that has to manage the development of the models, the generation of the models, and then another work package merely related to decisions. Now, let's go to the phase in which we generated the model. So the automated generation and validation of our models. This is the main concept. We start from a physical system that is operating. You see here in the picture. We have sensors in this physical system, and then we collect data by sensors that we store in some place here. These data are aggregated, okay, and manipulated, okay. Why we are manipulating this? Because we want to derive the models from the data. And so the goal, the purpose is what we call system mining. And then we have the logs, what we call event logs. And then using a schema, what we do, we generate a kind of ontology we call system knowledge graph, okay? That is a kind of ontology representing and putting into relationships the data that we collected from the physical entity. And then starting from the system knowledge graph that you see here, we apply system mining algorithms or system discovery. to generate what? We generate the mathematical model of the system that generated those data, of the physical entity, that if in this case is a chemical plant. You see here a graph. A graph is a mathematical representation of this manufacturing system. And then after we have the mathematical representation of the discrete event system, then we can map the graph to, let me say, a set of classes in a simulation platform, and then we can transform the mathematical graph in a simulation model that you see here. In this case, for here you see conveyors, machine, and so on. And this for us is representing what we call the digital twin. Okay, the digital twin mainly in our project is a discrete event simulation model that we generated starting from the sensors that we have in the physical entity. Okay, so this is the main concept of the project. So from sensors, from data, we generate a simulation model. And then we will use simulation model for green decisions. Here you see the external services of the digital twins that can be provided. We are not demonstrating all these kind of services, but here you see a classification based on the feature. We might have a service that is description based for diagnosis or monitoring. The first is looking to the past, the second into the present. We can establish a service based on prediction. So it's a forecasting service. We are looking to the future. And then we might have services based on prescription. In this case, I'm always looking to the future. Let's say for control purposes or for design purposes. In AutoTrain, we are demonstrating mainly the prediction based with the forecasting and the prescription based with the control. Here you see the platform in which you have the legacy systems of the company here in the top, in the bottom part, the industry here, and then we have industrial data connectors. And then starting from here, we have the AutoTwin platform. Mainly, this layer is related to the data. And these data are also using the IDS data space framework. And then we have the different components for generation of the models, for decision making, and so. Okay, I don't explain now all the models, all the components, sorry. So this slide is to mention that in addition to the automated generation, in addition to the management of the data into a common data space, IDS space, and the green decisions, we are also managing the gaps. So as I said in the beginning, we want to lower the skills needed to develop and maintain a digital twin. And so we have also some tasks related to skill management that I won't mention in this presentation. Let's move now to the use cases that we are studying in our project. The first use case is related to the recycling of the plastic, and we have a plant for plastic recycling from PET, and we have sensors, we have a lot of data, and as I said, we want to develop the digital model and so the simulation model of this plant. Second is the sterilization process in an hospital. And you see here the medical devices for surgery are here, and then to decide to repair, and this is a loop. Okay, you see a very short loop, or refurbish or recycle, these are longer loops. And we have sensors in the sterilization center, and we are generating the simulation model for this center. The third one is related to battery in electric vehicles. And here you see a rack. These batteries are for mainly are energy storages. And this is not a system digital twin, this is a product digital twin, so we want to estimate the residual life at the state of charge of the battery. Now, some project results until now, after 2 years. Mainly the project is dedicated to develop the components for managing the internal services of digital twins. So model creation, alignment of physical to digital, model validation, a model update, the update of the prediction of the simulation model, and we are not managing the prescription check, but more or less from model creation to prediction update, we are developing the components. Here you see the activities from this flow. We start from data that are collected and stored, and then we prepare and enrich the data. These are events data, mainly. And then we have mainly a discovery digital, sorry, we discover the mathematics of the digital twin, and then we translate into a software here, and then we have a validation component. So we validate what we discover here in the learning phase. If it is not valid, we move to calibration, and then we do this cycle again and again and again. These activities automatically are very difficult to develop for any kind of system. So we are including to embed in our data representation and also in the model representation what we call domain knowledge. So what we know about the system, and so we can facilitate the discovery. Here you see the components in which we have mainly the core, the data core is what we call system knowledge graph that has different layers that I will show later. And it will use a manager for the different functionalities related to data. And then mainly we have a component for system discovery. So we are mining from data the system, the mathematics of the system. And then we move from math to objects thanks to this component. And then we have another component that is used to discover causal dependencies from data. And this will help to understand a little bit better the system we want to discover. And then we move from objects to digital model, and then we are able to simulate. Here you see the layers of the system knowledge graph. We have the raw data layer here, and then we have the domain data layer in the second level here. And then we have the layer of the model. So the model that we discover goes here. And then we have the policy layer, which policy the model is using in order to process the flows, and the performance layer. These are examples of data integration and transformation that the system knowledge graph manager is doing. For instance, here you see that these records are related to two types of records, object record and event record. And then you see here that this record, then that we store in the raw record layer, then it is transferred into, let me say, more valuable information, because this record has an event here, and this event is observed into this activity that was a load of a machine that was started. An operator was doing accomplished this activity, so this event, you see it was operated by, it was using a kit with a certain number, so it is acting on this kit, okay? And then to this event, we have another event that is following the first event. And you see here this arc that is a kind of precedence graph that we are introducing. So from flat data layer, we are creating this kind of ontology so that the discovery will be easier. And here you see some functions of the SKG, mainly of enrichment and cleaning, in which we make a data integration. We may add the domain knowledge that we know in advance. We manage duplicated data. We inference missing data, and also we inference missing objects mainly. This is particularly in the case of plastic. And this is an example in which, for instance, we don't have a sensor to check this event, but with the system knowledge, then we can enrich, and then we can add this node in our system knowledge graph. And so we are enriching and cleaning the data. So from these data that are flat mainly, we generate a graph with a much more meaning. Let me check the time. Sorry, I have to control my time. This is the result on causalities from data that are, let me say, events that are stored one after the other. We have a partner, or IBM in this case, working on explainability, and is able to move from a process view to a causal view like this. This is a causal graph that we can infer from the data, and this is useful to develop the mathematical model. And now here we are to model discovery. From the knowledge graph, we have 3 types of model discovery. First, a graph mining, mainly an adapted process mining algorithm, let's say in this way. And so we derive a graph model like this with stations and arcs. We have a discovery of a PetriNet like this. These are the same system, but with different representations, but the 2 systems are equivalent. The third module is automata discovery. Here in this case, we have a production line producing pizza, and this is the automaton from the perspective of a pizza, and this is the automaton from the perspective of a station. So you see that with the same system, and this is the digital model, that is a pizza line, we generated different perspectives of the same system that we can use in a synergic way, and also with the different purposes. Here you see the graph mining procedure that first mine the topology, identify the operation. We have developed a state reconstruction based on the events. Then we mine the attributes, and then we export the model. All the models are stored into the system knowledge graph. Here you see the schema for the automata model layer and for the Petri model layer. And then we move from mathematical models to digital objects. You see here that all these models, mainly now we are starting, we have an automated procedure to move from graph to, let me say, a digital object in a simulation platform. This is, for instance, these are the properties of a cleaning station in the healthcare use case. And these are the properties of a cleaning buffer kit. A thing that I want to point out is that the simulation models that we are developing are interpretable. So we are not developing, let me say, a digital twin based on a neural network. It's not a neural network. We are developing physics-based models, okay? And so these models can be taken by the user, like this one, and can be modified. So they are interpretable, fully explainable, and can be modified by the users. After the digital tree, we have a simulation model. Then we developed a simulation optimization algorithm. We developed we implemented, because this technique is already available. It's called OCBA, for stochastic simulation optimization, but we embed it in the platform in order to choose what the best control policy to be used in the system. So we are using the digital twin to make simulations, and then we have this simulation optimization technique to choose the best policy. You see here from the twin to the optimizer, the exchange of information. And then here we are choosing the best policy, or at least with the budget that we have, what we consider the best. And then after we implement the policy, we develop a component that is doing mainly what is doing conformal checking. So it is trying to understand if the policy that we select as the best, and then we implement into the system, if the physical entity, the physical system is really following that system. You know, a circular economy is complex. Maybe not all are, let me say, following the control policy selected by the optimizer. But so we are doing conformal checking with this purpose. Here you see the kits in the healthcare system to be processed, and then the ones that have been processed. And here you see the violations per station over time. So what was different from the control policy? It's 40 minutes, good. So I will conclude saying that now we have, after 2 years, a platform that is managing data, is generating models, and is also managing models in the most automated way. It's not completely fully automated way, because we have a customization. Some models might need customization, but we have quite a good platform now that we are trying to test. All the code is available on GitHub. We have 3 use cases. The components have already been customized from the Chroma healthcare use case, and the customization is ongoing for the others. The fine-tuning of the models will be in the next months. And in the end, each use case will test the digital twins generated from the data. So we will test the accuracy, we will test how useful will be for optimization purposes, and so on. And customization, of course, will be important. So we try to assess the weight, how important is this customization, also to understand the business value of these models. I come back to the feature of the digital twin. If you remember, basic, advanced, we have 7 features, and what we are addressing. So it is digital because we are considering the main features of the circular economy. We can query the digital twin, we generate graphs, charts, table, everything digital. It is descriptive because we are catching with the mathematical models, so the graphs, the pepinets, the automata, the relations existing among the events, the time events, the resources, and the actors. It is synchronous because we can track and trace each item in the circular economy. And then, of course, as I said, we are working on the predictive feature. We make estimations, prescriptive, because we select the best control policies among a known set. It is adaptive because we change the model and the parameters according to the new data. And if we aggregate the information in a different way, we might have a different models or digital twins at different levels. Now we are here, you see we are in the last phase just for validation of the use cases. That's all. You see here the logo of the partners. I had 40 minutes. I think I'm on time. And I'm available for questions. As I said, I wanted to present the project results. Presenting all the project, I could not be, let's say, very technical. I hope you understand. But for each of the results that you have seen today, we might do a technical presentation.